Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, for the weekend about to start. Just pray that you be with us today as we study cyclic groups together. In the name of prayer, Lord Jesus. Amen. Okay, so what is the definition of a cyclic group? We've talked about this before, but not exactly. So before we proved a theorem back in, I think it was lecture 3, we proved that the cyclic, if you look at the subgroup generated by a specific element, right? So in a multiplicative sense, let me write it down here. So if G is equal to this, all right, so just to remind you what that means, 1a squared, dot, 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 and so forth, all right? If you can write G as being generated by a single element, then G is said to be cyclic. All right? Otherwise, it's not. Now, I look back at lecture 3, and I think that was one of the places I had a feeling like I made this transgression of assuming laws of exponents for you guys without proving it. I couldn't quite pin down where I'd done it. That was where I did it. In the proof of that we proved previously that inside a larger group, right, that if you have, let's say, G, it's always a subgroup of G, even if G is not cyclic. So this was a theorem we had back from lecture 3. All right, and then in the process of proving that, although I had A there, so this is always a subgroup for any element of the group. But when that subgroup turns out to be the whole group, then the group is said to be cyclic, and A is called the generator for the group. All right? So a little bit more here with generator. A. So today what we want to try to understand, is what's the structure of cyclic groups and what's the structure of their generators? What can you say about generators of cyclic groups? So let me just work an example or two here to get us started. If we look at D3, right, which we can write as 1r squared f rf r squared f, right, with the usual song and dance. Well, if you calculate the subgroup generated by R, what do you get? You get this guy. If you look at the subgroup generated by F, what does that give you? It gives you 1 and F. If you look at the subgroup generated by RF, you get 1 and then RF, right? And why just that? What happens if we look at RF squared? What's that equal to? Right. To be clear, this is because R cubed is equal to 1 in this context, right? And F squared is equal to 1, so that's where it loops back. This one, you see it's RF, right? And one of the identities is that this is R inverse. Excuse me. Oh, wrong way. Sorry. Idiot. This is R inverse, so we get R inverse, which is 1. So in fact, the element RF has order 2. All right. One of the things we'll prove today is that the order of an element is the order of the cyclic subgroup which it generates. That's one of the theorems we'll prove today. Of course, it's right here. Now let's see here. What else do we have? How about R squared F? Well, through a similar calculation, you can show that this has order 2 as well. So again, this is just like this. Let's see here. So we got R, F, RF, R squared F. How about R squared? What does that look like? What's R to the 4th? R again, right? Oh, look, so that's the same as this one, right? Now, what's the cyclic subgroup generated by 1? Yeah, this one's kind of boring. All right, so is D3 cyclic? No, why not?
You can't generate the whole group by a single element.
Right, we cannot generate the whole group by a single element. How do we know this? Brute force. We just calculated all possible, right, principal subgroup, all possible subgroups generated by an element. So D3 is not cyclic. Another example, you can look at the integers under addition, right? And the integers, right? You can either form, you could look at it as the group generated by 1, or you could look at it as the group generated by -1. Because if you let x, if you look at the subgroup generated by 1, what is this? Well, this is n times 1, right? Such that n is an integer. So this is the additive version of, so if we have additive, then what this means is NA, right? So this is how the cyclic subgroup is generated under addition, right? By repeated addition, which is multiplication by n. And if you look at -1, well, it's the same song and dance, right? I mean, what is this? This is completely, I mean, that is exactly the integers, right? I mean, obviously. And likewise this, it's not hard to see that this is, again, the integers, right? So all right, well, silly examples aside. So what does that say about the integers under addition? They're cyclic, right? Another example, we could look at Z4, right? It's not hard to see that 1 gives you what? 0, 1, 1 plus 1, 2. Okay, I mean, anyway, I mean, this thing I just did, we could just as well up the ante a bit, right? I think you can pretty easily see that Zn is cyclic, generated by 1, right? So 1 is always a generator for Zn. And for pretty much the same reasons. Well, let's see here. What else could you do? What happens with 2? We get 0 and then 2, and then when 2 plus 2 is 0 again here, right? So that's out. What's the subgroup generated by 3? Three plus 3 is 6, which is 2. 2 plus 3 is 5, which is 1. So right. So Z4 apparently has 2 generators, right? What are the generators for Z4? Right. Right. So in Zn, in fact, we can always see that pattern as well. 1 and -1 are always generators. But the question is, what else is a generator, right? Okay. So, for example, you could look at Z10, right? And it's not hard to see that Z10 you can either generate with 1, you can generate with 3, you can generate with 7, or you can generate with 9. However, these are the generators, all right? But if you look at any of the other numbers, you don't get all of Z10, right? So for example, the cyclic subgroup generated by 5 is what? 5 plus 5? Yeah, that's it. Or if you look at 6, what do you get? 6 plus 6 is 12, which is 2. 2 plus 6 is 8. 8 plus 6 is 14. So you get the evens, right? With 8, what do you get? 0, 8. 8 plus 8, 16. 16 plus 8 is 14. 14 plus 8 is 22. 22 plus 8, 0 again. Right? Yep.
Does that mean all relatively high numbers generate the set?
Maybe. Yeah, I think you can start to see the pattern here, right? I think you can see the pattern. Like Jess said, relatively prime numbers are the generators for Zn. We should prove that, though. One more example. Get it out of my system here. Examples are important. I better do it over here. U10. All right. 1, 3, 7, 9. If you look at U8, what's U8? 1, 3, 5, 7. U20. 1, 3, 7, 9, 11, 13, 17, 19. All right. So you can show that U10 is equal to, for example, the subgroup, it's generated by 3. To see that, this is what? 1, 3, 3 squared is 9. 3 times 9 is 27, which is 7. There you have it, right? And U10 also has, you can also generate it with 7, okay? But on the other hand, 9, what happens with 9? 9 times 9, 81, it's 1 again, right? So 9 is not a generator. How about U8? Let's go to town here. So if we look at the subgroup generated by 3, what do we get? 1, 3. What's 3 times 3? 9. Oh, no. So that's it. Well, that's not going to do it. How about 5? 5 times 5? 25. Oh, also known as 1, mod 8. That one's not going to do it. 7. 1 and 4. Oh, 49 is 1 mod 8, isn't it? So, apparently not cyclic. So the groups of units don't have to be cyclic. In one of the problem sessions, we worked this out. Not cyclic. Took us a little bit more work, but you can show that that's also not cyclic. I show every element in U20 has either order 1, 2, or 4. All right. All right. So here's some examples just to get us started, to give you a sense of what we're looking at, trying to figure out what's a generator, what's not, what can we say about cyclic groups. But before I get into that, I do owe you a theorem that we should have proved back in lecture 3, really. Or I should have made it a homework problem. Oh, maybe you should be glad I didn't think of that. But actually, I think you'll forgive me if I don't actually do the proof here in front of you. I'm just going to state it. You can read the proof in the notes. It's pretty clear, I think. So let G be a group. All right. And G an element of the group, and M and N integers. All right. Then 1 G to the M times G to the N is equal to G to the M plus N. And 2 G to the M to the nth power is also G to the Mn. I think I have a typo in my current, I say I did this in lecture 3 homework. I think it's actually in the lecture 2 homework. This is for problem 5. In problem 5, I prove a lemma. It's proved in the so-called lemma to my solution of problem 5. It's 3 pages for me. There's a bunch of cases, lots of tedious induction. Once you know that, it's actually not that hard to prove too. That's about a half a page. I have it on page 41. I'll let you read it. If you have questions about it, you can ask me, okay? But I really want to just use these, all right? And focus on the content of chapter 4 today, so I'm going to do that. Any questions about this? So just so we're clear, you're free to use these. However, you're also responsible to prove these, but I wouldn't ask you to prove one in its entirety on the test. That wouldn't be fair, because that would be all I got to grade, because it would take you the whole test time to construct the proof properly. But I could choose some like subpart of those proofs as reasonable test questions, right? Like if I focus in on M and N both positive or something like that, it makes a reasonable question. If you guys would like, I can prove 2. People want me to prove 2 or not? Okay. Well, if you do want me to prove 2, you can put in a request for the next problem session. Oh, man. Ah. Well, you remember them. I'm spoiled in here. We have too many boards. Let's see here. In most rooms, I just give up on the whole idea of leaving the example up and referring to it later. You know? Okay. Theorem, finally. Let G be a group. And A an element of G. If the order of A is infinity, then I and J distinct implies that I to the A is not equal to A to the J. If, on the other hand, the order of A is equal to n, a positive integer, then the subgroup generated by A is given by 1. We're using multiplicative notation here. A squared, of course, dot, 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 A to the n minus 1, where AI is equal to AJ if and only if what? N divides I minus J. All right. So let's prove this thing. Start with the infinite case. So suppose the order of A is equal to infinity, right? And I is not equal to J, but AI is equal to AJ, right? So I'm working towards a contradiction. What would this say then? Oh, and for the sake of without loss of generality, what can we without loss of generality, suppose I is greater than J, right? One of them has to be greater than the other. So let's just suppose I is the one that's greater, right? This statement is symmetric with respect to I and J, right? You can replace I and J with J minus I here, and it's the same thing. If n divides 3, n divides minus 3, or whatever. All right, so so this gives us, what do we do? I'm going to take this equation right here. I'm going to multiply both sides by a to the minus j. Right? And then what am I going to do? I'm going to use the laws of exponents. By the way, I should give this a name. This theorem will be referred to as laws of exponents. It's named after Mr. Laws, of course. Let's see here. So this is a to the I minus j. Well, the standards for comedy are low today. This is equal to a to the 0. I'll take it, though. But a to the 0 is, because j minus j is 0, right? Fine, I'll write j minus j. Are you happy? So that implies, of course, that a to the I minus j is equal to e. And what does that tell us? That tells us that the order of a is at most I minus j. Which, of course, is a contradiction, right? So what does that mean? Any questions? This part I got through without, I think, even looking at Galilean. I was just like, la 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 la, this makes sense. The next part, it's not much harder, but it does require a little bit more technology. So here we go. So suppose that the order of A is equal to n, where n is, of course, finite. All right? Then suppose that you have a sub I equal to a sub j. Upper I, I'd say sub, listen to me, a upper I, a upper j, right? For 1 less than or equal to j less than I less than n. Again, I want to look at distinct, well, anyway, I'm looking at distinct I and j here. So what can I do? I think my, okay, yeah. This is, I need to do, this is not going to give me that immediately. It's a step on the way towards proving that, all right? So here we go. So then what can I do? Multiply by what? You might guess a to the minus j, right? To obtain what? by the same algebra we just did, a to the I minus j equals to e. Right? What does that contradict? So that says that the order of a is less than or equal to I minus j, right? But what does that inequality right above that say about the relation of I, j, and n? Yeah, but what is this? Yeah, exactly. So I is less than n, and j, so this is definitely what? Smaller than n, right? So this is clearly a contradiction to the order of a equaling n, right? So what does that mean? So basically by proof by contradiction here, we get to suppose what? Given this condition, we have what? Right, so hence for 1 less than or equal to j less than I less than n, that implies what? That ai is not equal to aj. So if there's going to be hope for those being equal, it's got to be that the I and j are further than n apart, or they're at least n apart, right? The a sub I and the a sub j can't match up again unless we're at least n powers apart. All right, so continuing on here. So oh man, sad marker. Well, if I can bring it back to life. Let k be an element of the integers, all right? Then by the division algorithm, what do we get? There exist q and r, a quotient and a remainder, in z such that what? K equal to q times n plus r, right? Where what? 0 is less than or equal to the remainder is strictly less than n. Then we can look at this. So observe. If we look at a to the power k, what is it equal to? Qn plus r, right? Which by the laws of exponents is a to the qn times a to the r. See where I'm going with this? So you can rearrange that as what? A to the n to the q times a to the r, right? But what's a to the n equal to? By assumption, this is e, right? Because we said the order of a was n. So a to the n is e. And so e to the q, a to the r. But of course, e to the q is just e again, right? So this is just a to the r. So, consider then 0 less than or equal to r less than or equal to n allows what? R equals to what? What are the possibilities for r in here? Of course, 0, right? 1, 2, all the way up to what? N minus 1. And what does this calculation right above show? It shows that anything, right? If you look at all possible powers of a in this context, they always can be rewritten as a to the r, where r is the remainder of k upon division by n. So the possible list, right, a, 1, a squared, so forth and so on forever and ever. It's just 1, a squared, a to the n minus 1. Right? What's left to prove? So there's in part 2 here, there's really there's 2 parts, right? The one is that the cyclic subgroup generated by A is this list. And the next thing is basically that these are distinct. But that's said in this way, right? A sub I is equal to A sub j only if n divides I minus j. If you think about what this says for that list, it says that these are distinct, right? There's no 2 things in there that are even n apart, right? In terms of powers. So, where are we? All right, so suppose, I'm running out of, I guess I better work over here now. So continuing. Suppose A upper I is equal to A upper j for some I and j integers. All right. Then we can do what? Same thing we did last time, right? Multiply by A to the minus j. What's that give us? Right? A to the I minus j is equal to E. And then we can do what? Apply the division algorithm again. And what's the division algorithm tell us here? We're going to apply it to I minus j. All right, so I minus j can be rewritten as, excuse me, Qn, right, plus R. What's the condition on R? It's between 0 and n, not inclusive, right? Could be 0. Then what do we do? Then we calculate, basically. So you take this division algorithm, right? And we come up here. I know that E, right, is equal to A to the I minus j. So then what? I can trade I minus j for A to the Qn plus R, right? And then, laws of exponents. This is A to the n to the q times A to the r, right? But what was the deal? A to the n is E, right? So that's just what? Just A to the r again. Excuse me. Then what? So just to summarize here, we have what? A to the r is equal to E. But what does that say about R? R equals n. See, R can't be n, right? So this says what? This says that since the order of A is n, right? There's basically, it forces this implies then that R has to be equal to 0. Otherwise we contradict, right? Because otherwise we'd have a power which when we raise a to it, we got the identity for something less than n, but that contradicts n being the order of a. All right? So what's that say then? So far is equal to 0, what do we have? We have I minus j equals to qn. Therefore, n divides I minus j. So we have shown that a sub I is equal to a sub j implies this, right? What's this down here show? This is in black. I mean, I believe this proves that they're distinct. So, anyway, before I start coughing like a fiend, I'll just ask if there are any questions. Like me. Oh, okay. I guess fine. So this is actually, that's an if and only if, right? Which part of it have we taken care of? This part or this part? We assumed what? A sub I is equal to A sub j, right? And we proved that. So we've only done this part. It still remains to do the converse. The converse is actually easier. So conversely, suppose n divides I minus j. What's that mean? I minus j is equal to what? N times k for some k, right? If n divides I minus j, that means that I minus j is a multiple of n, right? Thus, a to the I minus j is equal to what? A to the nk, which is equal to what? A to the n to the k, which is equal to e to the k, which is equal to e. Hence, a to the I minus j times a to the j is equal to e times a to the j, which gives us what? So it's not hard to prove that AI equals to AJ follows from that assumption. Really just laws of exponents and what it means for the order to be n. Excuse me. The proof I just gave is pretty similar to one that's given in Galilean for theorem 4.1. The key really is just applying the division algorithm appropriately and keeping track of what you got to prove. So now, with this theorem in hand, we can say a number of interesting and really beautiful consequences, right? Corollary. For me, 1.6.13. Of course, the numbering in Galilean is different. But if G is a group, and A is an element of the group, then the order of A is equal to the order of the subgroup generated by A. Now that's called a corollary to the theorem. I've been reading some in this other abstract algebra book by Rotman. And one of the fun things about Rotman is he mentions the meaning of words and so forth. It's like one of his hobbies, I guess. And he mentions in there the word theorem is, I forget, I think ancient Greek. Basically, I think it was ancient Greek. It basically means to contemplate. So when you say theorem, it's kind of like, hey, check this out, right? And then corollary is, I think, Latin for flower. So in ancient Rome, it was popular to give flowers as like gifts, right? So basically the theorem is giving us a gift. It's giving us flowers. That's what a corollary is. So this is a gift given that work, you know? The theorem we had to work for, this not so much. So proof, if the order of A is equal to infinity, right? Then notice that this, right, is 1, A inverse, A squared, A to the minus 2, and so forth and so on, right? And these are distinct, right? How do I know that? The theorem, okay? That's part one of the theorem. Says that if the order of A is infinite, the powers which are generated from A are distinct. So it goes on and on forever and ever. You can count. Well, we don't have enough fingers, right? So infinity, right? Not finite. At least I don't know. I've never met a person with infinitely many fingers. Perhaps you could argue if a person was perfectly spherical. But I don't know. If on the other hand the order of A is equal to n, then what the theorem just showed is that the subgroup generated by A is 1, A, A to the n minus 1, and these were distinct. All right? So, count. The order of A is equal to the number of things there, 1, 2, 3, n, and of course that's also equal to the order of A. So Leah, you asked if I could prove that the order of the element was the order of the subgroup in like a help session about a week ago. And this is why I refused. Because we're going to do it, but it takes some effort. It's obvious. From examples, this is obvious, right? That this is the pattern. That the order of the element is the order of the subgroup, right? But this is what it takes to prove it. Where was I? Another, make sure I don't lose track of my papers. Let's see here. Another corollary. (1.6.14). All right, if G is a group and A is an element of the group with the order of A equals to n. I'm really getting tired of writing this. Anyway, an integer, positive integer. Oh, the grammar here is somewhat suspect. We probably should just cross out this if and say suppose. There we go. I did make a B in freshman English. So there you go. I guess it was warranted. A to the k equals to E. Well, in my defense, it was a B plus. But anyway, I transferred it, so it didn't matter. A to the k equals to E, then n divides k. So let's see here. Let's read this again. So you got a group. It's got an element of order n. If you can take that element and raise it to the power k and get back to the identity, it must be that n is a divisor of k. In other words, k has to be a multiple of n if this happens. Proof. Right? So suppose the order of a is equal to n, and also that a to the k equals to e. Thus what? A to the k is equal to a to the 0, right? What's that say? So the order is n. I have a to the I equals a to the j, but I equals k, j equals 0, right? Thus n divides I minus j. But what is I minus j here? I minus j here is k minus 0, right? Therefore, n divides k. Oh, we proved it. Yeah. So what does this mean? So how do we apply that? I think I can erase actually more here. You know, how does this help us as we're thinking about our search for generators? So here's a thought. Suppose you have the order of A is equal to 3. All right? Then the only way you can get A to the K equals to E is what? K is multiple of 3. Right? Let's see here. Let's make it a little more interesting. Suppose you've got a to the 50th is equal to e, right? What does that tell you about the order of a? Now, before we had the theorems we had today, what have we been just saying? We've been saying what? We've been saying, okay, well, if a to the 50th is e, we can say this much, right? We can say that the order of a to the 50th is what? Excuse me, the order of a. I'm an idiot. The order of a is what? It's at most 50, right? Because by 50, we're back to the identity. But now we get to say so much more, right? Because this corollary says what? If some power goes to the identity, that power has to be a multiple of the order of the element. So since you know how to find prime factorizations of integers, you can enumerate the possibilities, right? What are the possibilities here? The order of a could be what? You could have a squared equals to e, right? Or you could have a to the what? A to the 5th equal to e, right? The 10th. The what? The what? Divisors of 50. Yeah. That's okay. 25, right? Of course, yes, it could also be 50, right? And for while we're at it, it could also be that A is E, right? But those are the possibilities, right? So check this out. What if we had that A to the 26th was not equal to E? then the order of A is equal to what? The order of A is always something. Or it's infinity. I didn't say A to the 26 was E. I said A to the 26 was not equal to E. Oh, I'm sorry. And I also mean that A to the 20, to be more, you're, fair enough, you guys are confused. Say A to the J is not equal to E for J less than or equal to 26. That's what I mean to say, sorry. It's automatically 50, right. So if you think about finding orders of elements, right? If you know you're working in a group of whatever order, you get to a certain point, you don't have to keep calculating because you know at that point it has to be a generator for the whole group. You don't have to actually get all the way to the power of the group, the order of the group, to show that because of this theorem. This is very labor saving, used wisely. Well, that's a pretty good place to stop. We'll pick back up. I've got a little bit more in this, what I call Lecture 6. Lecture 7, basically next class we'll finish Chapter 4. So, thanks guys.